stream here and go ahead. You're first at it. Hmm. Yes, that is what we are going to do today. Because it's an extrapolation that I know last semester folks had some difficulty with, and given that we don't have a whole lot of time left, I figured it would just make it easier on ourselves if we went over it as a group, and then you could implement it directly. So yeah, yeah, we're definitely doing that today. Yeah, piecewise coding is tricky. You have to see like several examples to be able to generalize, I think, how to set them up from a novel situation. Which is why there's two in here, and this will give you a third. And this is something that to this day I sometimes struggle with, like trying to check my logic. Okay, does this make sense? But yeah, we'll go over that. So, yeah, I moved it. It was going to be yesterday, and it's now next Monday. Practically speaking, the only difference that that makes is when people who have already submitted it can see whether their answers are correct. That won't now happen until next week. But there's no deadlines in terms of points lost. I just want everyone to get their stuff in by the end of the semester. That's really the only hard deadline, so to speak. So, all right then. Well, that seems like that's a good place to pick up. I've had several questions about the first part of homework 4 as well, the groups and the group mean differences, and so I wanted to go back over that. So let me share my screen, and then we'll move on to the piecewise coding. Let me find, where's my screen share? Screen 2, here it is. So what I have open is the Word document that I posted. What was this? Formative assessment number 5, and I had started typing code into. I'm starting to add to it because the only part that I didn't do was the group means themselves. And I've had several questions about that, so that I thought it'd be good to go over that. So here's what, yeah, nice loud thunder. This is going to be fun. Here's what the model looks like. So in homework 4, you have section 1 asks you to predict golf scores from differences across groups. And so there's 4 groups. It said to make the control group, which is labeled group number 1, as your reference. And so the predictor variables that I'm going to put in the model, I've just labeled group 1 versus 2, 1 versus 3, and 1 versus 4. And here was the code that we did last week in SAS to create those groupings. So if original group is 1, then this is the pattern of values that the new variables takes on. Because my group 1 is the control group, which is supposed to be the model reference, that's where all of the predictors have to be set to 0 for that to work. For each successive group, then after 1, each of the contrasts turns on corresponding to which group it is. So if it's group 2, then the contrast variable that's supposed to distinguish 1 from 2 turns to 1. Likewise, if it's group 3, this one turns to 1 instead, group 1 versus 3. And then group 1 versus 4 turns to 1 if we're talking about group 4. And that selective turn it back to 1 happens in Stata in this step here. The order is backwards. It says turn it to 1 if group is this, but the logic is exactly the same. So any questions on just that much before I go on? No. Okay. Then this is what I started typing here today is how do we get the means for each group, and then how do we get the mean differences out of the model? So again, here's the model. Just pasted it down here. If I were to take this model and fill in the values for the predictors that correspond to each group. So the values that would go in, for instance, for group 0, it would look like this. Group 0 is coded 0 for all 3 of these, and so it works out that the only thing you need to form group 0's mean is just beta 0. In SAS, or I have a sort of a hodgepodge here of Sass and Stata. It's either constant in Stata or intercept in Sass. Let me fix that just one second. For these two, there we go. The analog, how you would ask for that equation, we highlight both of these here, is right here. So intercept 1 means start off with whatever the intercept estimate is. I need one of those. Anytime you are creating a predicted outcome, the intercept has to be included. Always, always, always. Then I wrote out each of the potential additions to the intercept that would result from my predictor variables as placeholders. So the first time through, each of these variables would be multiplied by a 0. So I put zeros in. So this line should already be given to you in your output as the intercept. There's nothing added to it. Group 2, however, is something that you'll have to ask for. So in this case, I add the value 1 because that's when group 1 versus 2, for if it's group 2, that takes a 1 instead of a 0. The others stay at 0. And so then in the estimate statement, or the lincom, I need to change that one to match. So the 1 goes behind the variable that would be coded 1 if that's the group you're looking for. So here's, if I do group 3, I don't need a beta 1, but I do need a beta 2 because that's for the contrast 1 versus 3. So then over here, I need to get rid of that one, set it back to 0, and put this one on instead. Can you all see me typing? Okay. All right, is this helpful to see the logic? Okay, thank you. Our estimate in Stata the same. Yes, the only difference is in Stata, rather than the word intercept, it's underscore CONS for constant. And Stata also makes you put in the multiplication and addition that is implicit here explicitly. So if I were to do, for instance, this line as a lincom, let me grab that, put it underneath so we can compare. I can see you guys. You guys are frozen now. Okay, am I back? Okay. You can hear me. Okay. Okay, yeah, some of you are frozen and some of you aren't. It's a very weird dynamic here. Okay. I have an idea. To preserve bandwidth, I'm going to shut off my video and have you guys do the same. That way, if we get disconnected, then hopefully there'll be less freezing. Okay, I'm still streaming, so that's on. Okay, it looks like we're okay. Okay, I'll say all the videos are off. It looks like everybody's still here. Good. Use the chat window, please, to let me know if I freeze again, because I can't tell. And yes, I'm not going to sing Frozen, Cheryl. Once a semester is enough. I don't need to torture everybody like that. Let me see. Let me get my screen share back. All right, let it go. Yeah, I know. Okay, here we are. So we're doing a lincom before the internet crapped out on me, as predicted. So the other piece besides the asterisks that convey the multiplication is to put in plus signs. So in between each of these is a plus sign as well. And if we get disconnected again, by the way, I'm going to post this after class once it's done. So let me back this up a little bit here just to show the the correspondence. So the equation for the mean itself, this thing right here, the way that Stata makes you write it is a lot more transparent. So the betas multiplied by the values literally happens in the lincom as well. And the plus signs that separate each of these things that are being added together to form a linear combination show up in the lincom as well. So there's a much more direct mapping as to what the lincom is trying to do, is to write this equation. It's just replacing whatever the betas are going to be when it calculates what the mean is going to, what is the predicted mean is from the model. Okay, that was Jean-Paul. Does that answer your question? Yes. Okay, good. And you guys can unmute yourselves and talk, certainly. I know it's weird to be all blank. I'm just worried about losing connectivity again. Um, so then that same statement, if you're going to be writing it for each of the other groups, then each of these zeros would selectively turn to ones. Only one in a row, though, for this coding scheme. And John Paul says, thank you, that was where I was stuck. Good, okay. The others, so yeah, the group means then you should be able to do with this recipe. And the group differences we had done before, that was already in the document. So I'll finish this up with group 3 and 4, and I'll repost it and let you know via email once that is ready. So, all right. So there are a total of 4 statements. There are 4 means to be predicted by the model, and I believe the homework asks for all 4. Only 3 of them are statements that you have to write because the mean for the control group is directly given as the estimate for the intercept. The other 3 are linear combinations of the intercept plus the effect of the slope that denotes the other variable. So group 1 versus 2, for instance, has to be in the linear combination if you're talking about group 2. So yeah, so we start with group 2 being a 1, yes. And so then the next time, if we're doing this, let's see, group 2 mean, I copied this over and didn't finish it. If I did group 3, then that's that one. Group 3 in the label is that one. And then group 4, if I just want to do one more to finish it off, may as well. Group 1, the last one changes to 1 in that. There. Now we got them all. Yes, so this is for part 1 of homework 4. That's what we're working on here. Okay. All right. Any other questions on part 1 of homework 4 with respect to group means and group mean differences? Watching the chat window. Still streaming, that's good. Okay, nope, we good. All right, cool. Then part 2 is pretty straightforward. In that, all you had to do was fit a quadratic effect. You didn't need to make a new variable. So in that case, it was the effect of enthusiasm. And so to fit a quadratic, it's enthusiasm times enthusiasm. Let me see here. I started another, coding scheme. So we can do that one real quick. So if we have enthusiasm and enthusiasm times enthusiasm, make sure you spell that correctly, otherwise SAS will get angry at you. Enthusiasm, there we go. So on the model line in SAS, it would be model score equals that. In Stata, it looks a little bit different. It's regress score as the outcome variable. And in theory, you can copy this change the asterisk to a hashtag or a pound sign, depending on how old you are. And there's one more thing. You have to have a C dot in front of enthusiasm to make Stata do the math to create the multiplicative term. So it would end up looking like that. All of the things that I'm asking for in part 2 are given directly by the model. So there's no lincoms needed, there's no new variables that need to be created. So part 2 is the most straightforward of the 3. So this should be sufficient. The C dot, I think of it as like continuous variable, but I'm not sure that that's what that means. In Stata, there's 2 kinds of variables that you can have as predictors. There's C dot and there's I dot. C dot means it's being treated as a quantitative predictor, and you don't technically need it until you're trying to make Stata do math with it. So for instance, I wouldn't need the C dot except for this term right here. I dot is a categorical variable where it's doing some behind the scenes coding for you. So yeah, the C dot thing, you can pretty much just always use it. It won't hurt anything. Sometimes it will run without it. But when you're having it do math like this, like create this interaction term, then you need it. Okay. Other questions on part 2 of homework 4? It won't compute unless you have the C dot. Yep. In this case, it is necessary. And I believe I had it in the example 4 that goes with this because Stata would have given me an error message had I decided not to have it. All right, are we ready for piecewise coding then? Yes. Okay. The ones above should have a C dot. They can, they don't have to, because you're not asking it to do any math inside the model. All right, so let me pull up Excel here. I'm going to do some typing. So in the original data set, there is a variable called experience with mini golf that takes on these possible values. And I asked you to fit, let me get the exact instructions up here just for reference. And this is section 3 of homework 4 that I'm scrolling through. Create one predictor to describe a linear slope of experience from 1 to 4, and then create a second predictor to describe the slope of experience from 4 to 7. So we're fitting 2 slopes to describe the overall pattern of effect of this variable. So we got to build those. It said, hang on, the other part here, use experience equals 1 as the reference for the intercept. So I got to start there because that's where I know to put my zeros. Experience is 1. So the new predictors that I'm going to be creating, so I'm just showing the logic for now and then I'll do the code second. Because the instruction said make experience 1 the intercept, that's where both new predictor variables that I'm going to be creating, I've named them experience 1 to 4 and experience 4 to 7, are going to be set to 0. So the first predictor is going to index what the effect of a 1 unit change in experience does to the outcome, but only up to 4. So you can think of it as predicting differences among people with relatively low experience is more helpful in this case in your miniature golf score. So 1 more than 1 to get to a value of 2 is 1. Likewise, 2 more, 3 more. Okay. So the first slope looks just as if we had centered experience at 1 and just created that. That's what that needs to look like. So that tracks the effect of a 1 unit change in experience on golf scores up to 4. Okay, with me so far? Got one yes. Can I get some little thumbs nodding? Think so? Okay. All right. Then the other variable. that's supposed to, no thumb option without camera? Really? I guess that stands to reason. Bummer. Okay, well, I'll just watch the chat window then. And if the thunder stops, maybe we can turn the cameras back on. So the second variable, it's raining so loud I had to get my headphones. Okay, so that's not good. Jeff, where are you that it's raining that loud? Are you in Iowa City? Iowa City. Okay, I'm up in Coralville. I don't know which way the storm is moving, but we'll find out. All right. Where was I? Oh yeah, 4 to 7. That's what we're doing here. Okay. So experience 4 to 7 is going to start after 4 because it's going from 4. So I'm going to do a 1, a 2, and a 3. So I've got like two little like slopelets here. It's sunny in Chicago, Dre says. Well, congratulations. It was actually a beautiful morning outside. I went running earlier today and thought, wow, this is a perfect day. Of course, I had to jinx it. So my two slopes here I've got set up. There's the first one here is tracking the effective experience from 1 to 4. The second one is going to track the effective experience picking up from 4 and then going to 7. Now the question is, what goes in the off cells? The second slope is probably the one that's easier. Yep, it is 0 because it's not active yet. So essentially what's happening is that this slope is going to turn on. Hey, stop that. There we go. In the second half. And this slope over here needs to shut off. Yeah, so what I've helped a couple people troubleshoot. It doesn't go back to 0. What it does is shut off at the value that it last had. So it goes 3, like that. So we have the first slope being active until 4, and then it stops. So if you have a value higher than 4 on experience, the first slope is agnostic to that, doesn't pick it up. That's because the job of the second slope is to pick up where the first one left off and index further gains in experience and how that affects scores. So this is the logic that we're trying to then implement in the code. Try and make this a little bit smaller so we can see it next to the typing. That's what we're trying to do. Where is the other window that I was typing in? I have too many things open at the same time. Here it is. There we go. Put these two next to each other. Okay. So this is what it's going to look like as implemented inside SAS or Stata. So in SAS, I have two different commands that are going to do all of the coding for me. If experience is less than or equal to 4, so I'm going to tackle this part first. Then my new variable is going to be the old one, experience, minus 1. That gets me right there. So we're only focusing on these cases right now in the first if statement. The second one, experience 4 to 7, is 0 because it's not active yet. So the first line of the SAS code here, that line right here, gets me that much. Okay, I can't highlight them both at the same time. I give up. The second line then, if experience is greater than 4. So note that the first line covers 4 inclusive, less than or equal to. The second line then is greater than 4. So it's only going to apply to 5, 6, and 7. If it's 5, 6, or 7, then do set the first slope equal to 3 because it would have shut off. And then the second slope is experience minus 4 because 4 is where it picks up. So it's like 4 is the 0, so to speak, for the second slope. It's the reference point. And so then that picks us up that second part. So I will pause there. Questions? Is this helping? Dre was the one to ask first. Dre in sunny Chicago. Eagerly watching the chat window. Questions? Any of that you want to hear again? So we don't need to create a variable for experience. Yes, we do have to create that. So these two variables right here are the ones that the code is trying to create. I named them exp14 and exp47 because that's my way of trying to keep track of what they're supposed to mean. So this is how those two new variables would be created inside SAS. And that happens here. The new variable equals, and then how it is created from the old variable. And yeah, that does create the two, it creates the predictors and sets them equal to the values that they need in the same step. For stata, then I'm initializing both new predictors to 0 and then selectively recoding them. Thumbs up, thank you. And selectively recoding them. So if experience is greater than or equal to, or excuse me, if experience is less than or equal to 4, then the new variable is experience minus 1. If experience is greater than 4, then the first variable shuts off at 3. And if experience is greater than 4, the second variable picks up at the original variable minus 4. So I don't know how to do multiple things simultaneously in stata after one if, so I had to write two separate statements, but not such a bad deal. And so once you have those two new predictors in the model, created in the data set, they go directly into the model. So for instance, in stata, that would be regress score, if I can spell correctly, score, and then exp14, exp47. And if you want to add the C's just as a sort of a good habit, that would work too. In SAS, it would be just the variables that you created without anything further. Okay. Hearing rain, nothing that sounds too catastrophic. How are we doing? You can't see me, but I have my how are we doing hands open. Thumbs up from one person. Better. Okay. Question from the audience. I haven't tackled the results question for sections 1, 2, 3. Is there anything that's helpful to know? No, those should be pretty straightforward. It's asking you about directions of the slopes, so positive versus negative, and it's asking you about significance. So if p is less than 0.05, then the slope is significant. If p is greater than 0.05, the slope is non-significant. The only other trick is just what the standard error of a slope means. That is always the same thing. It is always how far off on average the sample slope is going to be from the population slope. So there's several questions that are literally the same thing, just as an attempt to burn that into your brain. P-value of 0.05, yes. So it's P less than 0.05. So if it were 0.05, then that's non-significant. Did that answer your question? Thumbs up. Okay. Yeah, I'm one of the few people that doesn't know how to do emojis on my phone. Like everyone else in the world sends me, a literal thumbs up or something, and I just type thumbs up into my phone. So this is making me feel better. All right. Now, other questions before we move on from this? I'm happy to repeat myself as much as needed. Am I still recording? I think I am. Yep, according to the software says I'm recording. So can you say again what you do the model step? So each of these models in homework 4 has score as the outcome variable. So this part is going to be the same no matter which section you're in. What goes after it depends on which section you're in terms of the predictors. So you would end up with, let me just put these together so that it works a little bit better. So in SAS, section 1 would be the contrasts that you made, 1 versus 3, G, 1 versus 4. That's part 1. Part 2 would be just enthusiasm like that, and then part 3 would be the new piecewise slopes that you made. The analog in Stata would be regress, lowercase regress, thank you word, the 3 slopes that you made. Enthusiasm would be the second part, and then the 2 new slopes that you made for the piecewise effects of experience would be the third part. Does that answer your question? Yes, okay, good. With the C, yes. The one where the C's are strictly necessary is the second one, but you can throw them on everything if you don't want to have to remember which is which, and it won't hurt anything. I tend to do that actually when I code in Stata. Oh, hang on, no equal sign. That's a copy paste error. There we go. So the first variable after regress is always the outcome. The variables that happen after that are the predictors whose slopes you're trying to estimate. Okay, other questions on homework? Think you got it. Okay. Well, if you don't got it, if you have questions, you can send me emails, screenshots. To be able to help you troubleshoot, though, I'd have to see what you did for code, and that way I can determine where the problem is. So just remember that if you're asking me to please paste that into the email if you could. All right, I will save this document then, and I will save this as well. Inside more locations where it's supposed to go. I love how it tries to like navigate to all the places I don't actually save to. All right, we'll do this later. Anywho, all right. You want to try video again? It's too weird just talking to my laptop with no one there. Can't handle it. Oh, that's so much better. All right, I'm hiding my own self because I don't want to see myself. It's very distracting. All right, welcome back. I think we're okay for now. So any other questions about coding for homework while we're on the topic? Okay, then how about we finish out the rest of lecture 4 and example 4, and then we'll be ready to do a new topic on Thursday. So the good news, folks, by the way, I know you have one whole homework remaining after this one. It's not going to be hard. There's only one new concept. Everything else is already stuff you know how to do. The thing that's going to make it different, what we're starting on Thursday, is the idea that you have more than one predictor in the model at the same time. Not just like different contrasts within the same predictor, but more than one predictor. And so then the vocabulary switches a little bit in terms of how you interpret their slopes, but otherwise it's all the exact same mechanics you already know how to do. Applause. This is applause. I like it. Yay. I was going to say spirit fingers or jazz hands, but applause works as well. All right, there we go. Then let's look at piecewise slopes. So this is the thing we started talking about last week. This would be a good place to revisit it, I think. So this is slide 29 of lecture 4. This is another example of piecewise coding. I've got this one to show you and one more after this. So this, just to recall, this is the effect of education in years. And I had hypothesized, based in part on sort of the knowledge of what education means, as well as this observed plot of means, that there would be one effective education, basically no effect, up until you graduate high school. Like that's the magic point. If you cross that line, then you should have more personal income. Likewise, if you can get past high school and acquire some sort of advanced degree, then you should be doing even better. So I wanted to fit a model to test that idea with one slope that basically I would expect to be flat that goes through this section here from 2 to 11. Another slope that goes from 11 to 12. So I think of it as like a bump, just an acute shift of one grade level. And then another slope that captures the increase in education after grade 12. So to do that, here's the logic, and then I'll show you the coding again in just a moment. First thing you got to know to be able to set up your codes correctly is where's the intercept. Now that's a decision typically you would get to make. I chose grade 11 in this case so that it would be the easiest to think about conceptually what graduating high school would mean above that. So grade 11 is my intercept, and I know that because that's where everything is zeroed out. So that's the model intercept will be the expected income at grade 11 because that's when all the predictors are coded 0. That's what I want. To move backwards from 11, then if you had grade 10 instead, I have a slope that becomes -1, grade 9 would be -2, 8 would be -3, and so on. So it's tracking less education relative to 11. The second slope then is off at that until we hit 12, at which case it picks up and turns to 1. The first slope shuts off after 11. It's done. It's only there to track the effect of education up to 11, and then it shuts off where it left off. So in this case, where it left off is 0, and that's why these are zeros all the way down. The second slope is 0 until it's active. It turns on at 12, and then it stays at 1 where it left off. So that's why these are all 1s. The third slope then is inactive until it goes past 12, and so it picks up at 13 here and indexes the effect of education after that. Okay. Does that make sense conceptually? Okay. Now how to get the codes to do it. Like it's a series of switches essentially. It's like the first one is active up until 11, then it shuts off. The second one kicks on from 11 to 12, and then it shuts off, and then the one picks up from 12 and moves on. So the codes to do that in either program here on slide 31. If education is less than 12, the first slope is whatever the value is minus 11. The others are set to 0. If education is 12, the first one has been shut off, the second one turns on, the third one's not active yet. And if education is greater than 12, the first one is still not active, the second one has turned off at 1, and the third one, it picks up where it left off. Education minus 12 creates the pattern that we have here. And then stata, I initialized each of these variables to 0 because that was the most common value, and then selectively replaced them. If education is less than 12, then the first slope takes on this value. If education is greater than or equal to 12, the second slope picks up a 1, and then if it's greater than 12, it picks up this value right here. Okay. The results then. So each slope is responsible for its section of the overall effect of education. So these were in example 4 in the handout as well, same numbers. So we have 3 slopes in the model working together to describe the effect of education. So first question, is the model significant? Meaning, do these 3 slopes work together to significantly predict the outcome variable? And that I know from my F-test. So I need to know, in order to evaluate an F, what the degrees of freedom are for the numerator, for the denominator. Numerator is number of slopes. Denominator is number of slopes that you could have had, but you didn't. And that is a function of sample size. So there are, in total, in this example, 734 people. I estimated 4 fixed effects in this model, the intercept that's always there, and 3 slopes. So that's why the degrees of freedom for the denominator, the second part here, are 730, because I used 4 things, and there's 730 left based on the number of people that I could have used but didn't. The F then is 47. I don't know what that means until I look at the p-value that goes with it, and that's significant. So 4 fixed effects, 3 slopes. So I'm counting the intercept because that's one thing that we had to estimate is in addition to the slopes. It's always there. So like even in an empty model, you're estimating an intercept. So at most you've spent 1 degree of freedom. In that case, at least I say you spent 1 degree of freedom. You may have 3 more in this case after that. MSE, mean square error or mean square residual, works out to be 159. That number has special meaning. Do you remember what it is still? I asked you this last time. It's a word that I like to ask you about in your homework. And this is where you find it. Mean square error, mean square residual, also known as, there it is, residual variance. Yes, variance left over. So all of the remaining reasons why some people make more money than others, aside from their education. Is that a lot? Well, 159, it's in $1,000 units. I don't know what that means. To help put that into context, I need to know the R-square for the model. So R-square, it works out to be 0.164 here. Remember, there's 2 different ways you can think about it. R-square is the proportion reduction in variance. So 16% of all the variance in personal income was explained by education. So this number that's left, this 159, that represents the remaining 84% of what we started with. The other way to think about R-square is how well the predicted outcomes from the model correlate with the real ones. If I take that R-square and take the square root of it, it works out to be 0.4. So I can say that the income that is predicted from your education is correlated positively with the income that you actually have at 0.4. And I know that that correlation is significant because that's the same idea as whether or not the model is significant. So what F test statistic is telling you is whether or not that R-square is significantly greater than 0. Whether or not on the whole, your 3 slopes in this case have worked together to create a significant prediction that's significantly related to the actual outcome. If not, it's kind of game over. All right, how are we doing? Okay, seeing the nods, that's a lot better than the chat window. I'm gonna be honest with you, I got to be you guys for a change last week. I'll tell you how tired I am of being stuck at home with my child. I actually volunteered to go to a faculty meeting. That is a new low. Like, because we were both supposed to go. And it's like, well, we both can't go. Do you want to go to the faculty meeting or do you want to play with Huey? It's like, I will go to the faculty meeting. And do you know what I got done during the faculty meeting? My nails. I was one of the black boxes. I made sure to put my yellow thumb up whenever a question was asked. But yeah, I sat there and gave myself a manicure. So I call it multitasking. So I could. He wants one. He periodically asks me if he can have his fingernails painted, and I tell him as soon as he stops sucking his thumb. That's the breaking point. So he has his toenails painted because I let that happen. But right now there's like one of them left that the paint like slowly chips off and eventually goes away. But yeah, I got my nails done. So multitasking. But I could feel like the how uncomfortable it was for the people talking because there's like 40 of us that are all black boxes, right? And you just say something and you wait and there's nothing. And I was just like, ha ha, it's your turn now. I get to be one of the black boxes who says nothing. But anywho, so is this feeling better as we go over things more? Like you could actually do this in your lives, maybe? Because that's the big picture question, right? Is if with these resources you could sufficiently recreate this when needed in the future. That's the big question, and what I'm op optimally hoping is possible. Um, so each of these then intercepts each of the slopes has a t-test that goes with it. That t-test tells us whether or not that slope in particular is different than zero, meaning that that contribution to the model is significant. So if we look at the pattern, beta 1, which is tracking the effective education from the minimum number of years up until 11, right? So if you didn't graduate high school, does it matter how far you got? Uh, this slope is not different than zero, so the estimate is minus 0.3, and that combined with the standard error of 0.6 gives me a p-value of 0.65. So well within expected territory, not significantly different than zero. So far, it doesn't matter how much education you have if you didn't graduate high school. That's what this slope being not different than zero is telling me. The effect size for it, if I were to get a standardized slope, and those come from either SAS Proc Reg or in Stata, if you add the beta option after your predictors, you can get the standardized slopes. That's the effect size. So yeah, this is a tiny, it's in correlation units. It's a very tiny correlation, almost zero exactly to 2 decimal places. If you, does it matter if you graduated high school? Yes, as expected. Income is higher by about $4,600. That estimate divided by the standard error gives us a t that results in a p-value of 0.01, which is significant. So yes, that estimate is positive. I have a standardized slope for it. It corresponds to an R of about 0.1, so it's a small effect. A D of about 0.2. D is standardized mean differences. So basically there is a 0.2 standard deviation difference between someone who didn't graduate high school and someone who did. And then what happens after that? Is more education better? The answer is yes. So for every year after 12, you gain another $2,000, which is significantly greater than zero. And the standardized slope for that is pretty big. So now we're up to about 0.36 in terms of a correlation metric. So of all of these, the effect of more education past high school is the biggest of the three. So note that one of these slopes is actually not helping us. Beta 1 technically doesn't need to be part of the model. If we were trying to make our model parsimonious, meaning get rid of extra stuff we don't need, Marie Kondo the model, can I say that? Yes. If it doesn't spark joy and if it doesn't spark significance, it doesn't need to be here. So the F value that's resulting from these three slopes, it's actually lower than it would be if the first one were omitted. Because when you have an F that's testing three things, what it's working out is sort of the average contribution of the three. One of the three is actually bringing us down. So if we wanted to, in theory, we could get rid of it. However, it complicates the interpretation of the rest of the model to not have that section of education accounted for. So it'd be like the intercept is anybody who has 11 years of education or less in that case, which is a little bit weird. So I'd say for the cleanliness of interpretation, I would leave it in even if it's not significant. It does help to sort of make the point that education doesn't help until you hit some sort of threshold. Okay, so here is what the model predicts. I made a picture to show the trajectory that is created by the intercept in these three slopes. And up until 12 years of education, I think the model does a decent job. There's a lot of noise on the low end, but it looks like it's capturing the tendency. But if I look at what happens from 12 up to 20, what do you guys think about the match between the straight line here that is predicted by the model and the data that are not quite a straight line? You, yeah, it should close, close. That's it. That's the word. Yeah. It needs to be some kind of bendy, right? So I thought, well, I'm going to try two tricks that I know, and I'm going to take this last slope here, and I'm going to add another model in which I add a quadratic effect. So it would be over high school times over high school as a fourth slope. And here's what happens. Okay, watch carefully. There. Did you see it? All right. That's the straight line. That's the bendy line. It didn't help. It's still not a very good fit. What if I tried to do exponential? That's the one that sort of goes up and levels off. There's that one. Nope. Yeah, and if you look at the R square, it actually went down a little bit. So it was 0.164 with just linear. It went to 165 with the quadratic. So no, this part of the curve is from 12 on, the model's not really doing a good job with. What I think needs to happen is that the end of this needs to become a piecewise model too. So I leave this out there for any of you who are bored. If you've got quarantine boredom and you want to try something new, try to fit a piecewise model that divides this chunk into sections, 12 to 16, 16 to 18, and then 18 to 20. Because I think that's actually what would be needed, and that corresponds roughly with additional postgraduate work in terms of the kinds of degrees you can have. So, all right. Questions on that part of the example? Okay, I've got one more example of a piecewise model that I want to show you, and this one is going to come up in your next homework. ... So I have a predictor in the same data set that is ordinal level of happiness. So there was like three people who claimed that anything worse than unhappy. So I rounded them into one group. And here's my scale. This is slide 36. X-axis is 3 says unhappy, 4 says neither happy nor unhappy, 5 is fairly happy, 6 is very happy, and 7 is completely happy. So let's not even worry about the fact that these people are likely lying to us, right? We'll just treat this data as valid. But let me ask you this. This is a thumbs up, thumbs down question. Are these numbers? Yeah, thumbs down on numbers. I mean, they're labeled that way, right? A 3 means you're unhappy, a 4 means neither, but they're not numbers. So this is a common practice, actually. You will find people fitting a linear slope through a predictor that's ordinal but not interval. I mean, inarguably, completely happy is more than very happy, but how much more? Oh, I'm breaking up again. Am I back? No, we're good? Okay. I didn't see everyone's face do this at the same time, so I figured it must not have been too bad. That's when I know that it's very bad. Just checking the recording. Yep, it's still the recording. Okay. I don't hear any more thunder, so maybe we're in the clear, so to speak. But yeah, you'll see this very common, that people will fit a slope through an ordinal variable, such as happiness. So I did this for demonstration purposes. I centered happy at 3 because that was the lowest value, and I fit a linear slope, and that slope is actually not significant. So it was a 0.7, but with the standard error of 0.5, that gives me a p-value of about 0.2. So 20% of the time, if the true slope were 0, I'd find a result like this. Not unexpected, not significant. So what if it were significant and I wanted to try and publish this result, that people who are more happy make more money? And reviewer 3 is not having it. Reviewer 3 wants to remind me that these are not numbers, and I shouldn't put a slope through something that's not numbers. So here's how I would answer them. Piecewise model. And Cheryl, you asked me a question like 2 weeks ago about coding these things, and I said that I would come back to it. I promise I'm coming back to it. The question was whether or not the piecewise slopes or the grouping variables would ever have a 1 in more than one column at the same time. Yes, they can. So I have set this up to track each of the successive differences in happiness with its own slope. So I have a difference of 3 versus 4, 4 versus 5, 5 versus 6, 6 versus 7. So the first slope goes from 3, which is my intercept, turns on, stays 1. Second one picks up where it left off, turns on, stays 1. Third one picks up, turns off. Fourth one picks up. So it's just working its way through each of the possible differences in happiness and looking at what one more unit of happiness translates to in terms of predicted personal income. So I want to contrast this coding scheme, what we're talking about here, this piecewise successive differences, with the one that we did at the very beginning of this handout, which was 3 groups, low, middle, upper. So you can decide how to set up your variables however you'd like. You have the power to make them mean whatever you want. The difference in what this coding scheme does versus something like this lies in whether or not the piecewise variables go back to 0 or whether they stay where they left off. In this 3-group example, we had low as the reference for the model. The first contrast was low versus medium, and the second contrast was low versus upper. The reason that these contrasts mean what they do is because of this 0 here in the upper value for the upper group in the first variable. The first variable distinguishes mid from lower and upper put together. The second variable then picks up and distinguishes lower from upper. So each of these contrasts represents the difference of low versus each other one. If I changed this value in the red square to 1, then the meaning of the second variable would change. Rather than having it be low versus upper, it would become medium versus upper, because it would then pick up where the first one left off. That may make more sense for something that's ordinal like this. So the 0, this coding scheme right here that we used in the first part of this example where it stays at 0, that's known as dummy coding. That's probably the most common. But if you have a categorical variable that is ordinal and you want to know what the effect of being part of each new category is, this type of coding scheme where they don't go back to 0, but they stay at 1 would give that to you. So the trajectory that we're fitting looks like this actually. This is the observed means. Income goes up a little, goes down a little, up a little, and down a little. So the model is going to capture each of those. Okay. Still with me? All right. So here's the code that you would do that in SAS. So for instance, if you look at the very last line, if it's group 7, then it's 1s all the way across. Because to get up to 7, you had to go through each of the successive steps to get there from 3. So the model's going to directly give you, the way this is coded, the difference of 3 to 4, 4 to 5, 5 to 6, and 6 to 7. I then asked as linear combinations differences in the slopes to know if the slope changed, so to speak, in between each jump. So is there a different slope from 3 to 4 versus 4 to 5, a different slope from 4 to 5 versus 5 to 6, and a different slope from 5 to 6 versus 6 to 7? If any of those were significant, that would suggest that a single linear slope is not a good idea. If the jump from 3 to 4 is different than the jump from 4 to 5, is different than the jump from 5 to 6, that's what linear says, is that they're all the same. If they're different, then one slope is not a good idea. If they are all the same, you could make an argument that a linear slope is more parsimonious and sufficient. Homework question. Here's the state of coding. Similar to what we've seen before, initialize to 0 and then selectively recode if we are greater than or equal to each of the thresholds or cut points, so to speak, and then linear combinations to get the differences in successive slopes as well. And I have the C dots in here too, just as a habit. Here's what happened. It works out that the only piece that was significant is this one right here, beta 3. People who say they are very happy relative to fairly happy made a little bit more money just on the underside of significance here. But on the whole, the model is non-significant. So in this case, I have 4 slopes. The average contribution of those 4 slopes, as given by my f-test, there's an f of almost 1. That's the bad one. It has a p-value of 0.3, so it's not significant. R square is only 0.007. So the 4 slopes working together to try to capture this 3 to 4, 4 to 5, 5 to 6, 6 to 7, they don't do any better than chance. So the model with happiness as a predictor does not actually predict income. The overall model doesn't work. Even though one of these differences is significant, the overall model doesn't, because it's being pulled down by these 3 that are non-significant. And that's it. Ta-da! We finally finished it. All right. Words. I'll let you read that. Questions. So just think of all the things you now know how to do in terms of asking questions about what predicts something. You know how to fit a grouping variable, create contrast to distinguish one group from another and put those in the model. You know how to fit linear effects of quantitative predictors. You've done that several times. You'll get to do that again in the next homework. And you know how to fit nonlinear effects of quantitative variables via either quadratic functions or piecewise functions. So that's really the main categories of predictors that you would come across in any kind of research. It should fall into one of those categories. Up to this point, though, all we've talked about is just one predictor conceptually. So in this last example, for instance, we had happiness as the predictor. It took 4 slopes to capture it, but it's still one idea. Likewise, education as the predictor is one idea took 3 slopes to capture it, likely more. Where we're headed next time is models with multiple predictors at the same time. So what would be considered multiple linear regression as opposed to just simple linear regression, or yeah, analysis of covariance also. So that's what we have left to do with our last 3 classes. Hooray! Can I get a hooray for the last 3 classes, if nothing else? Yes. Quick survey. Would you guys appreciate having office hours during finals week? Thumbs up. Yes. Okay. Well, I'm sure my husband won't appreciate this, but what my plan was is to just open up the Zoom room to both my classes during my regular class time. So that would be 12:30 through 4:30 on Tuesday and Thursday of finals week. Would that be helpful if I did that? Yes. Okay. If those times don't work for you and you're likely to want to ask questions during finals week, please send me an email and I can try to find some time to open up additional hours on either Monday, Wednesday, or Friday of that week. I do know that Cassie will not be holding office hours during finals week because she's got her own finals and projects to finish, but I don't. So I will be able to do that to make sure that everybody can get help to finish all of the work for the course. All right. Anything else before we adjourn for the day? No? Okay. Then office hours at 3:15 if you'd like. Otherwise, stay safe and I shall see you Thursday.